Hey gang, welcome to the Worksheet Solutions Walkthrough. For the worksheet, identify and complete the reaction for SN2, E2, SN1, and E1. Alright gang, so I'm sure by now you've had your fill of substitution and elimination both in the bimolecular and unimolecular senses. However, I like this worksheet because it takes everything we've learned, so much of day one up until now, and I threw a bunch of problems at you and you had to identify what kind of problem it was, and then you had to successfully complete the reaction. And at the end of the worksheet, you had two mechanisms or kind of justify how this occurred problems. So I know you're here for answers. Let's get to it. Okay gang, I'm going to be taking this one section of problems. It'll be whatever page we're on. So for page one, right, let's just take a look here. We'll figure out what reaction type, we'll list it over here, and we will predict the product over here. Okay, so for problem one, I hope you can recognize, so let's go through our mental checklist. We have a secondary substrate, we have I, which I minus is the leaving group. That's a great leaving group. So secondary, good leaving group, and I hope you're seeing our conditions over here. They are polar protic, and this is, weak nucleophile, weak base. So we don't see any high temperature, so this is screaming to me SN1, because we have a substrate, right, capable of forming a carbocation. Secondary carbocation can absolutely happen. We have a good leaving group, and we have a polar protic environment to facilitate solvolysis. So since we're doing SN1, remember, we're creating carbocations, so we are subject to shifts. So I think the very first thing we should do is draw our initial carbocation, which after iodine leaves, iodide, we have this carbocation secondary, right here. So can this carbocation improve itself? And the answer is yes, right? I can go ahead and illustrate a hydride shift, which would then show that we have this carbocation that we're working with, tertiary. Then my nucleophile, which is acetic acid, which we will be attacking from this oxygen, not the carbonyl oxygen, right? This is not the nucleophilic oxygen, it's this oxygen. So I can go ahead and predict my product, and it will look like this, okay? So you can see right here, obviously if you drew the mechanism, I would initially have this, and then I have a cleanup step, but I'm going to go ahead and not show that. Do I need to worry about illustrating that a racemic mixture is produced? The answer is no, because this carbon is not a chiral center, right? We have two methyl groups here, so it's achiral. Don't worry about showing a racemic mixture being produced by this SN1 reaction. This is our final product for this SN1 reaction, okay? Moving on to the second problem. And I hope you're seeing, okay, so we'll go through our checklist. Secondary carbon as our substrate, good leaving group in Cl-, okay? Polar aprotic, so again, polar aprotic, that means we're probably gonna be looking at SN2 or E2. And since we're secondary, right, that's that weird situation where it could go one way or the other, so we really need to see if we are dealing with a strong base or a strong nucleophile. And I hope you're seeing, okay, NH2-, that is a strong base. So we're going to be going with E2 here. Okay? So now that we've figured that out, we need to check a few things. So we have a ring. So we need to, okay, we have a ring and we have a small base, right? Small base. So with this small base, we want to form our Satzeff product, right? We want to make the most substituted double bond. That's the most stable double bond. And since this NH2- is small, it can actually get to where it needs to be. Now, because this is our carbon with the good leaving group, we can either eliminate this way or this way. Luckily, so the carbon we want to eliminate a hydrogen from to make the most substitute double bond is this carbon right here, because this is secondary, this is tertiary, this is secondary, this is secondary. So making a double bond this way, that's a more substituted double bond. The one thing we have to check though is, does it abide by the anti-periplanar rule? And the answer is yes. Our leaving group is a wedge. The hydrogen we are going to eliminate is a dash, so we have this thing going on. So I could even draw this quick little mechanism to show this hydrogen being abstracted, electron swinging down, and Cl- leaving. The one thing we need to be careful of though is when we form the double bond, This carbon's now planar. So that methyl group that was wedged, it is now a straight line. All right, 2 down, 1 more to go. So down here, I hope what you're seeing is secondary substrate, good leaving group, the tosylate leaving group. We're in a polar protic environment, so we can support the formation of a carbocation. So this is screaming either SN1 or E1, and we see high temperature, heat high temperature, right? So this is trying to favor E1. Now, depending on your class, right, some professors will have major minor listed. So what I would say is, since this is high temperature, this is someone trying to nudge you to predict the E1 product, okay? So what I'm going to do is I'm going to show you the E1 product, and I'm going to kind of list it as the major, meaning I don't know if it's actually the major, but that's what this high temperature is trying to, it's favoring elimination. So that's what we're trying to see done. So the carbocation we form after this leaves through solvolysis is this right here, secondary. So can we improve this carbocation? The answer is no, right? We wouldn't shift from secondary to primary, and we wouldn't shift secondary to secondary. There's no gain there. So the question is, do we make this double bond or this double bond? And the answer, right, is the most substituted double bond we can make. So we're going to make a secondary double bond that's di-substituted over the secondary primary double bond, which would be mono-substituted, okay? In the situation that you would have to label this major and draw an SN1 minor product, that minor product, right, it's still the same carbocation, right? But then we would have attack of the ethanol here as well as here. So if you had to draw SN1 and label it as a minor, that product would look like this. And I'm going to use the squiggly, but it would be a racemic mixture like that, okay? So what I'm saying is that I'm going to go ahead and say this is what the problem is calling for. But if you are tasked with drawing major and minor, make sure that you draw the correct SN1 product, and in this case we do have a stereo center, so make sure you show it's a racemic mixture. Either draw one and do plus an enantiomer, or do the squiggle. Either works. Okay, gang? Page 2. Okay, gang, on page 2, 4 more problems. So if we look at the first one up top, we have a primary substrate. We have a good leaving group in Br-. We have acetone as a solvent. So this is polar aprotic. So we are probably thinking SN2 or E2, right? No solvent caging going on here. So, and then we have OH-. So with the fact that we have OH-, which can be either a good nucleophile, or an OK nucleophile, or an OK base, we're polar aprotic, but we are primary, right? This is pointing to the SN2. Our substrate is not hindered. So SN2 is what is going on in this first problem. Now remember, the considerations we have for SN2. You know, we have to be worried about stereochemical inversion. However, at this position right here, we are not attached to 4 different things. This is an achiral center. So what we actually just need to do is swap out the Br for an OH. Our product will look like this. 2 carbons off of the aromatic ring, the benzene ring. This is our product here. So a nice, quick, easy SN2 problem on page 2 to start. So if we go down to the second problem. So again, if we look at our carbon right here, it's primary. Okay, so very not hindered. We are polar aprotic, and we have something that's, you know, just like oxygen almost in the same family. So again, because this is polar aprotic and we are very unhindered, and this is an OK nucleophile, I'm also saying SN2. Okay, however, right, we have stereochemical ramifications here. We can clearly see this is a chiral center. We are attached to 4 different things. So chlorine is our leaving group. Our arrows will look like this. However, we need to make sure we invert our stereochemistry. So just because our lowest priority group is facing us, we can do this really quickly and easily. Chlorine's highest priority, the carbon chain is second. Then we have the deuterium, because remember, deuterium is hydrogen with an extra neutron. So we look S, but we're actually R. Okay? So what I like to do is, since we will be sticking on this sulfur attached to a methyl group, and that's going to be our highest priority group, I'll show you a trick. And again, you need to be very careful how you do this. It doesn't work in every scenario. It has to be the right scenario. But if I go ahead and just swap out my leaving group with my nucleophile, you will see, again, if we assigned R and S, first priority, second priority, third priority, we look S, but we're actually R because our lowest priority group is facing us. But what I can do, because we need S configuration here, we need to actually be S, I can do a single switch of these groups. And when I do that, right, let me make sure I update my configuration assigning. We look like S and we are actually S. So just make sure, it can never fail you to assign R and S, right? Even if you just get everyone structurally hooked up the same way, right? Make sure you actually, even if you do a simple swap of your leaving group and your nucleophile, right? And you have everyone attached the same way, just assign R and S, and if you don't have the configuration you need, right, you haven't changed it, just do a single switch and then you're golden. Please use your stereochemistry knowledge. Just because we're in a different unit doesn't mean it goes away. Okay, so now this problem right here. I hope that so if you look at this problem, I hope you're zeroing in on this right here, and you've already mentally said, this is E2. This is such a big and bulky base, even with primary carbons, it's gonna do E2. So we have a strict base here, right? It's too big to do substitution, it's too large, so elimination is what it's going to do, okay? So when we look at our substrate right here, which is secondary, right, we do have a good leaving group and we're polar aprotic. So I did jump the gun, but everything checks out for elimination by molecular, E2. So we need to, because we're a ring and we can't, we need to check the anti-periplanar requirement. Because we are big and bulky, we want to ideally make the Hoffman product, the less substituted product. But I hope what you can see is, no matter if we're looking at this carbon above or this, either next door neighbor, we have the same kind of substitution. This is a tertiary carbon, this is a tertiary carbon. So we don't really have a choice. There's no less substituted double bond. They're both the same. However, we do see that one is wedged and one is dashed. So we see a situation here where one's going to work and one's going to not work in terms of the anti-periplanar requirement. So because bromine is dashed, we need a hydrogen that is wedged. We see we have a dashed hydrogen here. These two are cis-periplanar. Aha, but up top, this is the hydrogen we will work with. It is anti-periplanar. So we will go ahead and grab this. Electrons will swing down. We will kick off bromine. So we will form this double bond, but be careful. So we didn't touch anything down here. Double bond is there, but make sure this methyl group is now planar. Make sure to reflect that. Do not keep that methyl a dash, okay? So to round this out, let's go through our checklist. Down here is our substrate. I know there's a lot of wedges and dashes going on, so be careful. We're attached to a carbon here and we're attached to a carbon here. So this is a secondary substrate and good leaving group in Cl-. We have just methanol. So I hope you're seeing this is polar protic. We are secondary, so that supports carbocation formation. We don't see high temperature heat. So this is going to be SN1. Now remember, we need to be careful of shifts and we need to make sure that if we produce a racemic mixture, we need to reflect that. So let's have solvolysis occur, and I'll draw the carbocation we initially form over here. Didn't touch anything up top. So once this leaves, we actually have a planar situation. So I'm going to convert the wedges and dashes here to straight lines because this is sp2, it's planar, okay? Now, can we shift the carbocation? This carbon up here, 1, 2, and 3, it's tertiary, so the answer is yes. We can do a carbocation shift. Now, I designed this problem because not only did you have to make things planar when you created the carbocation, you have to make them planar when you shift. Now, don't worry about what you made planar at first. You can't predict what that will become, but this is, that is the result of this shift. Just keep this straight lines, but you must make this planar up top, okay? And it's at this point that methanol attacks. Like this, or from below. So, the way I would draw this product is just keep that deuterium like that, keep the ethyl down there, straight line, but we need to make sure we dash an OH, and I don't know, you can wedge the methyl if you would like that. Let me, and then plus, we need the enantiomer, so deuterium, attach that, whoops, let's do it this way. There's the methyl group. Oh, whoops, this is supposed to be, I apologize. Methanol, O-methyl, right? O-methyl. O-methyl, and the ethyl. So this was a little bit complicated just because solvolysis occurred, you had to make some things planar. You shifted, then you had to make more things planar. Then you had to reflect the fact that this is a racemic mixture. Okay, gang? All right, page 2, goodbye, hello, page 3. Moving on to page 3, we're ending our complete the reaction problems. Okay, so gang, if we take a look at our first problem, we can see secondary substrate, we have the tosylate leaving group, so good leaving group. We're polar aprotic, so polar aprotic, SN2 or E2. Secondary good leaving group, polar aprotic, and what we're dealing with, our kind of nucleophile or base, is NH2 minus. Okay, so now NH2 minus, super strong base. So in the secondary situation, this is going to be E2. NH2 minus, super strong base. We're a little bit sterically encumbered, so we're absolutely looking to snag a proton and create an alkene, a double bond. Okay? So, in this situation, right, this is a small base. So we will be looking to make the SATES-F product. Now, remember, our criteria for E2 is the anti-periplanar requirement. So our leaving group is a wedge. However, right, this would be the Hoffman product if we eliminated a hydrogen from here. We want to eliminate a hydrogen from here. However, in this current conformation that the problem is given to us in, the hydrogen we want to eliminate is cis-periplanar. That's a no-go. So what we need to do, which is something we can't do when we have a ring, because when you're on one side of a ring, you can't rotate the bonds to be on the other side of the ring. But with straight line, structures, Newman projection showed us, bonds are always rotating. So what we can do is we're going to have to rotate some bonds here before we predict our product. So what I want to do is I want to go over here. What I need to do is a double switch about this carbon. I need this hydrogen in the dashed position. So what I'm going to go ahead and do is going to wedge this OTS. So what I'm first going to do is switch the hydrogen and the methyl, giving me what I want in terms of the hydrogen, and then my methyl would be here, and I'd have this ethyl group, but I've only done a single switch, so I've actually inverted my stereochemistry, which is no good. But what I can do from there is switch the methyl and the ethyl to then, I've done a double switch. These two structures are equivalent, okay? But now I have the hydrogen where I want it to in terms of performing E2. So if I look over here and I finish out the problem, I can grab that hydrogen, swing these electrons down, and boot the tosylate. Now I can draw, and again, the methyl is kind of redundant because a line over there would just be to a CH3, but double bond here, ethyl up here, and then one carbon over there. So as you can see, that's the product we need based on having to rotate the bonds and make sure that you don't leave that ethyl group wedged. It needs to be planar because it's part of a double bond, which means that carbon is sp2 planar. Okay? So again, remember, you can only do that rotate the bond thing for straight line structures, not rings. Okay? So, moving on to the second problem. If we look at our substrate, we are primary. Okay? Very not encumbered, sterically speaking. We have a good leaving group in Br. We are polar aprotic. So polar aprotic, primary, and the fact that our nucleophile or base is cyanide, which comes from HCN, which is a strong acid. This is a weak base. So weak base, primary, polar aprotic. This is looking like SN2. We don't have a good base to rip a proton off. We're polar aprotic, right? So we're not doing solvolysis. So forget SN1 and E1. We are absolutely doing substitution. So and we are dealing with a chiral center, so we need to make sure we invert our stereochemistry. Okay, so luckily our lowest priority group is facing away from us. So one thing we can just really easily do off the top is just assign stereochem. So we are R, right? We look like R and we actually are R, okay? So one thing I can do, because we're booting our highest priority group and the CN will become our newest highest priority group, let me just swap out the cyanide where the bromine was, okay? You'll see that even though we do have a tie between the carbons here, we're triple bonded to a nitrogen, so the CN, the cyanide wins, the nitrile wins. So we look like R here, and we are. So one thing I can easily do to make sure we get S is just flip a pair, D and H. So if we really wanted to reassign again, just to verify that that worked, right? 1, 2, and 3. We look like R, but our lowest priority group is facing us. We are in fact S, okay? SN2, easy. All right, so right here, this problem. I hope you're seeing polar protic, secondary, good leaving group, high temperature. This screams favor E1, okay? So I'll do a major of E1. So I'll do E1, and then in parentheses, I'll do minor SN1. If you, again, would be prompted to draw both. But the carbocation we're going to work with is this one right here, right? Because bromine would leave in solvolysis. No shifts, nothing to worry about. The alkene, the E1 product we would make, looks like that. And again, we don't have to worry about any stereochemistry, right? This isn't a chiral center, so we don't have to do any racemic mixture nonsense with the SN1 product, should you have to draw it, but that would look like this. It would just be an OH, just an alcohol. But this, let me actually box these to avoid confusion. This would be what I would say the major product is because of the fact that we have high temperature, okay? Last but not least, to complete the reaction section home, we have a primary substrate, good leaving group, polar aprotic. This is azide ion. I threw this on here just to make sure you remembered. Azide ion is a good nucleophile, not a base in any sense. So this is just good old SN2. No chiral center here to worry about. This is a simple replacement. You can just attach it like that. Super easy, nice way to cool off to complete the reaction section. Okay, gang, to finish this worksheet, we have two kind of like mechanisms or, justify why this happened. So let's just finish strong. I know it's a lot of problems, but let's do it. Okay, gang, in page 4, we have a mechanism problem. We need to draw the arrow pushing mechanism for how this reaction proceeded. So I hope what you're seeing is we are in the presence of strong acid. We have an alcohol, so we could, well, it's not a good leaving group because, we can see it is the leaving group because it's not present in the product. We can absolutely have this alcohol grab H+, protonate itself up to OH2 plus water, good leaving group. It can leave, we can have a rearrangement, and that's how we can have the product over on the right. So, before we get ahead of ourselves, or at least I get ahead of myself, let's just start with what we know, and let's see the oxygen get protonated. Okay, so oxygen picks up H plus, and what once was an alcohol is now OH2 plus, water ready to leave. Okay, so through salicylisis, water will leave. We're in a polar protic environment, and now we have a carbocation. Okay, so of course we need to pause and say to ourselves, can we improve this carbocation? The answer is absolutely yes, which aligns with what we're seeing in the problem statement, right? I could absolutely draw this wedged hydrogen because this is a tertiary carbon next door, and I can illustrate this hydride shift, the hydride moving from the tertiary, the hydrogen from the tertiary carbon moving to the secondary carbon. So draw that over there. If I even asterisk this hydrogen, I can show it over here now. I now have a planar methyl group and a positive charge on that tertiary carbon. It's now a carbocation. And Br minus bromide, which has been waiting oh so patiently, can now attack right there. And if you're wondering why there is no stereochemistry present, it is because while this carbon is attached to a methyl group and a bromine, I can even put that there if I wanted to. This, if you want to think of it, these groups right here are identical. So, there's no point of difference. They're the same. So this is an achiral position right here. No need to show racemic mixture because there isn't one. Okay, one more problem. Tough it out with me, gang. You got this. In our final problem, we have to show the air pushing mechanism, basically justify why we're seeing the behavior up top, even though, so this is an E2 reaction, right? However, with this small base, why are we seeing the Hoffman product and not Zaitsev, right? That's pretty much what we're trying to investigate. Why Hoffman, not Zaitsev? Okay, so I hope what you are seeing is that our substrate carbon right here, the secondary carbon with the small base, the most substituted double bond would be going this way. It would be tri-substituted. However, the hydrogen we need to eliminate that position to do so is a dashed hydrogen, and it is cis-periplanar to our leaving group, right? We have a this situation, not a this situation. So in a straight line structure, we can handle that by rotating the bonds. However, on a ring, up is up and down is down. You can't change that. So this elimination is not feasible. So we have to look elsewhere, and our only other neighbors next door, and we do have two hydrogens to work with. Obviously, we don't want this one, but we do want this one, okay? So to show the mechanism, I think the most appropriate way to do that would be, obviously we need to draw the ethyl group, it's part of the structure, but you would expose the hydrogen that is anti-periplanar. You bring in your base, you show the base picking off, abstracting that anti-hydrogen. You swing down the electrons, and then you kick off the leaving group, and you flex one last time by drawing the product. Okay, gang, thank you for sticking around for what I know was a long, intense worksheet solutions walkthrough. I hope it was helpful. I hope you got the answers you were looking for. If you're watching this video, that means you've donated some money to jOeCHEM, and I can't thank you enough for supporting the website financially. I hope this website has been the resource you were hoping to find to help you conquer carbon. And I'm glad you're using it now, and I hope you're using it towards the end of OChem. But if anything, I hope to see you all in the next video.